We want to start off this section by talking about the idea of function arithmetic. Basically the idea that we can take two functions and add, subtract, multiply, or divide those two functions. First, we want to introduce some notation. Our first statement here, we have the expression f plus g of x. What this notation means is we want to take a given function f of x and then add the second function, g of x. Essentially meaning we would just add up all the terms between those two functions. Similarly for f minus g of x, we would just want to take the difference of all the terms in those two functions, or at least the difference of any like terms. We have f times g of x, which means we would just be taking the product of that first function, f of x, times g of x. And then we can also have f over g of x, meaning we want to find the quotient of that first function, f of x, divided by g of x. In this process, we also want to make sure that we're establishing or identifying the domain of these resulting functions. In order to find the domain, what we want to do is find all restricted values for 1, the original function f of x, 2, the original function g of x, and then also look for any restricted values in the resulting function. That means that if a value is restricted in f of x, it's also restricted in the resulting function, and the same would be true for g of x and any of its restricted values. We can take a look at this process in example 1, where we're given our functions f and g. We want to find in part A f plus g of x, meaning we want to take that quantity 2x plus 1 and add that second expression 4x minus 3. In this case, we can simply drop those parentheses, there's nothing to distribute through, and look at combining like terms to get 6x minus 2. Our original functions f and g have no domain restrictions, and neither does our resulting function, so the domain for this function will be all real numbers, or x is in the range of negative infinity to infinity. We can also look at evaluating f minus g, which would be a very similar setup. In this case, we would have 2x plus 1, but now we would be subtracting that second function, 4x minus 3. Here we need to make sure that that negative gets distributed to every single term in that second function, giving us 2x plus 1 minus 4x plus 3. And then combining our like terms, we would get negative 2x plus 4. F and g have no domain restrictions, neither does our resulting function. So our domain in this case is again negative infinity to infinity, or all real numbers. In part C, we're taking the product of f and g. So this means we would want to take that quantity 2x plus 1 and multiply by 4x minus 3. Expanding this out would give us 8x squared minus 6x plus 4x minus 3. Combining our like terms then would give us 8x squared minus 2x minus 3. Our resulting function is a polynomial, so still no domain restrictions, meaning our domain would be all real numbers, or negative infinity to infinity. In part D, we're taking the quotient of these two functions, meaning we would want to take 2x plus 1 divided by 4x minus 3. and then see if there's anything to simplify, expand out, or combine. In this case, there's no additional work we can do there, so this is our final answer. But now we do have a domain restriction. We have to make sure that the denominator of this resulting expression can't be equal to 0, meaning x can't be equal to 3/4. So we could state that our domain would be -infinity to 3/4 union 3/4 to infinity. Or we could simply state that we have a restricted value where x cannot equal 3/4. From here, an additional question that can be asked for each of these would be to evaluate the given function for a specific number. For instance, we could be asked to find f plus g of 3. This would simply mean we want to take our resulting function, f plus g, which in this case was 6x minus 2, and evaluate it for x equals 3, which in this case would give us 16. Nothing there really changes from our standard process for evaluating functions. It's just recognizing that notation and knowing then which function we should reference to evaluate. In part C, if we were asked to evaluate f times g of, let's say in this case, 4, we would look at that resulting function for f times g and evaluate it for x equals 4. Which would in this case give us 117.